Hello, guys. Can you hear us on Zoom? Zine, can you hear us?
Yes.
Okay, perfect. Okay, we're starting in a minute.
Yeah.
Okay. Sounds good. One to six.
Okay. Huh?
Okay. What do I like?
Wait, what are you doing? What are you doing? Wait, what are you doing?
Just taking control. The scene. How do I maneuver?
Just this. Just to the left, yeah. Guys, we're starting the bootcamp right now. If possible, we go from the slides in Piazza. So you can open like a slide and follow along.
Yeah. So, hello everyone. Welcome to Homework 2 Bootcamp. Hello everyone. Welcome to Homework 2 Bootcamp. And this bootcamp is going to be focused on convolutional neural networks. And so in this session, I'll guide you through the first part of the homework. And in this part, you will be implementing various components of the convolutional neural network using NumPy. So let us start with considering resampling. So in this section, you will be implementing both upsampling and downsampling for one dimension as well as two dimensions. So what exactly is upsampling? So upsampling means that you're trying to increase the size of the input, like either, and downsampling would be like the exact opposite of upsampling, wherein you're trying to reduce the size of your input. The thing that we need to take into consideration is that there should not be any loss of information. And in particular to this section or the homework, we do not recommend making use of for loops because when we are working with NumPy, like the NumPy library has a vectorized nature, and NumPy is like optimized for handling array operations, and like effectively we are applying the array like operations on the array at once. And these vectorized operations, they take use of the advantage of like low-level optimizations as well as parallel processing. And therefore, this leads to like faster computation when in comparison to using for loops. So we have like two methods here that we can see that you can utilize for resampling. One is you can look up np.cron. So np.cron is a numpy function, which is essentially finding out the chronicle product when we have two matrices into consideration. So basically the output would be output also would be a matrice, which is found in such a way that the first element of the matrix A is multiplied with the entire of the matrix B. For more information, you can look up to the NumPy documentation. And alternatively, another straightforward method that you can implement is using array slicing. So this functionality, it is supported in NumPy, and it allows you to define a slice of the matrix along specific dimension or axis. And you can also get to specify the start, end, as well as the step size. And as per that, you can like extract certain portion of your matrix. So we have covered array slicing in depth in the NumPy fundamentals recitation. You can definitely refer to that. And another thing that you need to take into consideration is that you need to like try to figure out the shape of you need to consider the shape when you are performing both upsampling as well as downsampling. So by looking at the output shape, you can figure out how you're going to make use of np.cron or array slicing. And another thing to take into consideration is that you need to save the shape in forward method. This will be helpful when you are writing your backward method as well in case of both upsampling and downsampling. So after resampling, we can take a look at convolutions. And you can do convolutions in two ways. One is by using nested for loops, like multiple for loops. And another efficient way that we would recommend is making use of tensor dot. And we suggest making use of tensor dot because in comparison to using for loops, it is faster. And moreover, it also takes into consideration like issues like broadcasting and even matrix multiplication. So the homework to part one write-up, it does include a section on tensor dot, and it is in the appendix. And you can definitely refer to that for more information. And we'll be covering some portion of understanding tensor dot right now in this bootcamp as well. So tensor dot basically is a function in numpy that helps us simplify convolution, and it does help us simplify convolution basically in reducing the number of for loops which you will write when you're coding your convolutions. And like as the name suggests, tensor dot basically is a dot. Tensor dot basically is computing a dot product, and at its core, it essentially does element-wise multiplication and summation. And another thing to note is that tensor dot is not going to perform the entire convolution. It is only going to take care, or it is only going to perform one step in the entire operation of convolution. So basically, when we have a kernel or filter, we are going which is being like overlapped on an image, tensor dot, how do we usually go about it is that we are going to perform element wise multiplication and summation, and that is going to result in some output value for us. So whatever is this element wise multiplication and summation, tensor dot is going to perform exactly that for us. And so by this, we see that tensor dot essentially is not like eliminating all of the loops. It is just decreasing the number of loops that we are making use of, like when we are implementing the element-wise multiplication and summation. So essentially, when it comes to conv1D, we require only a single loop. And in case of conv2D, we would require two loops. And like if you are tending to use more than these many number of loops, then there is like something wrong with the tensor dot implementation, even despite if you get the answer right. So we can take one example which helps us explain the functionality of tensor dot. And here we can see that we have an input X, which has dimensions A comma B comma C. And we have another matrix W, weight matrix, which is having dimensions P comma Q comma R. So essentially, when we are performing tensor dot, we look at the dimensions along which the shape matches. So when you are doing tensor dot operation of the input X and the weight matrix, here we are taking into, as seen on the slide, we are taking into consideration that B is equal to Q and C is equal to R. That is, along these dimensions, the shapes are similar. So when you perform tensor dot, when you're considering the tensor dot operation between the input matrix X and the weight matrix W, we see that the output will have a dimension which is that of the unmatched axis. So you see the output is having a shape of A comma P. And we need to make sure that uh, there is at least one axis along which the shapes are having matching dimension, and there is no such specific thing that on how many axes should have matching dimensions, but yeah, the minimum is like at least one axis along which the shape matches. And this exact approach we will make use in convolution, as we see that we have a filter which is going to like focus on a segment of the input. So in case of one dimension, like a single for loop is used, and we are moving through that exact single dimension from left to right. And at each index, we have a filter which is placed on or overlapped on the input image. And essentially here is where the convolution operation is happening. And we are going to like slide the filter from left to right. And what we are doing is like we are basically iterating over each index of the input. We place the filter and then we are making use of the tensor dot operation. So basically whatever element-wise multiplication and summation that you are performing, that you are going to replace with the tensor dot operation. And this you are going to continue for till the end of like the dimension. And yeah, so another important thing to note here is that printing the shapes in your code when you're like performing tensor dot operation is really helpful. Maybe we can consider another example in the next slide. So we can see a matrix which is having shape a comma x, like a, x, c, and y. And we have like another matrix which is having like shape x comma p comma q and y. So basically we need to look at the dimensions where the shape is similar. And also like here we can see x is matching and even y is matching. Another thing to note is that it shouldn't be like when you're like matching these shapes, they should be like in the same dimension. It can be anywhere. So when you are considering the output, the shape would be like eliminate all the dimensions where you are having like similar shape. So the output would essentially have a shape of a comma c comma p comma p comma q. So like essentially in the same order. And the next part is like we can consider like conv 1D and conv 2D. So essentially conv 1D and conv 2D are are exactly the same except for the number of dimensions. In conv 1D we have like a dimension of 1 and 2D is 2, and everything is exactly the same. But you need to ensure that like when you're transitioning from conv 1D to conv 2D, you need to take care of the extra dimension, and also like you need to take care of something extra when it comes to conv 2D. And the 2p1 write-up like has good enough depictions and write-up which will help you analyze and visualize all of these sections as well. And the next portion that we have is pooling. So essentially, as you will come across the lectures, you will find out like we have like some basic pseudocode which is given, which will help us explain pooling, which is both mean pooling and max pooling. And on the basis of this pseudocode, you can like further develop the logic. And this is one section of the homework, like in terms of part 1, wherein you might need to make use of loops. And you can also make use of np.max and np.unravel index when you want to try to reduce the number of loops, because more the number of loops, the slower time, slower computation time. But for this particular portion, when it comes to pooling, like it is okay to make use of multiple loops. And yeah, I think the next portion will be taken by Harshit.
Hey guys, so now we're going to talk about gradient propagation in CNNs. So here you can see here that the input, we can consider that to be A, and assume that we have 2 kernels. So for each of the kernels, you're going to have one single output. That's why you see 2 different channels there. So in order to find out the backward propagation for this, later on in homework 3, you will have to draw activity diagrams for that. This is basically a start to that. Here you can see that you need 2 maps in backward for DLDZ, and you can basically, instead of that, if you look at this activity diagram, so the influence diagram, you will actually have to see that input A affects the output in this sort of way, because you have 2 kernels and then you're going to get 2 different outputs. So any small change in the input A will cause a change in both maps. As a result, what you need to do when computing the gradient backward of output Z is you have to sum it across both the channels. which are there. So you have two different kernels and then two output channels. In the code, when you write backward for DLDZ, you're going to have to sum it across the different channels that you have. One of the tasks in this homework is to write a scanning MLP using a CNN, using convolution layers. So here's an example to sort of understand that better. So in the appendix, we've given you much more extensive examples to understand that. You have to write a simple scanning MLP as well as a distributed scanning MLP. Professor said that he would host a special office hours for that because usually we have a lot of questions on that. And no matter the question, the examples we give, there are certain nuances there. So in order to make up for that, we'll post about that. So here you can see that for a convolution, typically for a convolution layer, you have a height and a width, which is you have a height of 3 and then a width of 5 here. But for every linear layer, as we've seen in like homework 1, part 1, the input has to be flattened and like this, so it would be about 15 elements. So consider that the MLP takes some input. Let's assume that it takes the first 3 rows and the first 3 columns. That would be 9 elements. If that is passed to the multi-layer perceptron, then you basically get 2 outputs. So let's consider that example. Now, and then you move it across the entire input like this. And what happens? So you're going to assume a kernel size of 3. For the linear layer, you would have used basically the flatten before you pass it to your layer, right? But that's what we did in homework 1, part 2, if you recall. We had to flatten it before it could be passed into the linear layer. So now how would you do this using CNNs? Because we all know how you have an input, you would just flatten it and then pass it into a linear layer. And then you get the 2 outputs of the MLP. That's what the specification is. And then you would move by a stride 1 and then get that. So essentially, what we looked at here was that for the first 3 by 3 kernel size, you would get an output of 2. And then as you go along, you're going to keep on adding it. And eventually you get an output like this. That's what would happen in a typical MLP. Now you have the linear layer and you know what you need to do. Now, how do you convert this into a convolution layer? So you can see that you have 3 input channels, which are 3 rows in the input. And then you have that is converted into an output channel of 2. And then you have a kernel size of 3. And then we moved it across by each column. That would make it a stride of 1. So in order to convert this linear layer from a 9, because we took 3 rows and 3 columns at a time, 9 input to a 2 output, you would actually give the input channel as 3, the output channel is 2, and then the kernel size of 3, and the stride of 1. So this is kind of important in almost every machine learning project that we've written, whenever you write convolution layers, because you would want to know what the shapes of the input and then the output channels need to be. So that's kind of a good exercise to find out what that should be going forward, especially in Conv 2D, but we'll get to that later. Right. So to summarize, essentially, we have 2 different tasks here: the distributed scanning MLP and the simple scanning MLP. And more on that would be given in the handout. Now let's move on to the next step. Here, finally, you will create a CNN model in homework 2 P1. You will call all the layers you've just implemented previously, and you will use the homework 1, part 1 linear and the activation functions that you've written. So one thing to note is that when you wrote your tanh function, since we use exponents in that's the formula of tanh, there might be some overflow and underflow. If you do get any errors with that, we do allow you to use np.tanh in that. The one thing to think about when you write your CNN model is that, so you would have written a bunch of convolution layers, which goes from input channels to output channels and so forth. You have to figure out and then you're going to feed that into a linear layer. So you have to figure out when you're converting that from the linear to the convolution layer, what the size should be. So that will basically be a rows and a columns value. And that is basically figured out by writing out what the input channels or output channels of each of it are and what the output shape needs to be. All right, thanks. Now we'll move on to homework 2 P2.
Just as an introduction to cover up,
I know that all of this that we covered for 2P1 might seem very new because probably most of you all might have not had time to go through the write-up. But our hope is with this introduction that you all at least feel familiar with the different concepts and terms that will be covered in the write-up when you all start reading it, right? So you all don't feel completely lost. Also, the second benefit is you can definitely go over this bootcamp again once you do start doing the homework and encounter these problems that we've discussed. So that then should again tie in along with the lectures and help you out.
Thank
Yeah,
you, Sean.
now we'll start with part 2.
All right. Hello, guys. I'm Kate, TA for this course. We are proceeding with part 2 for the homework. Before we start this, we'll do a little reflection of everything you learned for homework 1, part 2. So if you guys can just open your, like maybe some notebook notes or whatever, and just simply ask this question. Just literally, what was the most challenging thing you think was in the previous homework, but you figured it out? Second, which strategies or resources you used and you think were very, very helpful? And finally, what do you think you would do differently if you could like start over from scratch? Could you just like, we have like 5 minutes. If you could just like each of you can think about it, maybe right? Because it will be very, very helpful for the next set of homeworks. Yeah, yeah.
I don't think I ever went to the boot camp semester because I just didn't have time to read it, so they not help.
You guys will be first who will be sharing. You guys want to share?
Us?
Yeah. Okay.
Yeah.
You share, just think about it. Yeah. No.
I'm gonna start.
Okay, guys, like, welcome back. We're just continuing this discussion. Guys,
All right, everyone. So let's get back and let's share what. So
The first-
anybody who wants to share, yeah, you all can raise your hand.
okay, yeah. No, I mean like first
Okay,
first
yeah.
would be we have a TA who's taken this course in the previous semester. So we can start with like asking the team member 1 on the yeah. We can ask first of all the TA from the previous semester who is taking this class. What was like, what do you think were the most challenging stuff last time?
I think from homework 1, part 2, probably the most challenging was because I had never done like deep learning or anything like that before. So probably for me, what was the most challenging that I was able to figure out was like what training a model looks like and like how to like make your data set, make your data loader, and like how to actually set up your network and just all the small things that like you have to do to actually train a model. And I think strategies and resources that helped me the most was going to TA office hours. You know, like now that I'm here, I can say that, but like sitting in your shoes, I know it's like hard to find the time to go, but I think going does help a lot. And like we are all here to like help. So definitely use us. And then if I were to do it differently, I would start sooner. And that is something that you guys will probably also face, but definitely start sooner for all these homeworks because it does make a difference.
That's great. Okay, any team wants to share some interesting insights? Any cool strategies that you want to share with your peers? Yeah.
If not,
Yeah. Do you guys, okay, who wants to share? Anything at all? Team number one on the first, like, what do you guys discuss? Anything, any interesting things?
Communicate with our teammates about our evaluation. Like what kind of tests have you tried? That's really helpful.
Yeah, this would be very, very helpful in the second homework. When you have to do much more ablations, communication with the team is very, very important. Yeah. What do you think? Josh, yeah.
I mean, I think the thing that helped me most was TAs. Just because I have a lot of head knowledge about these things, but I don't have like a programming background.
Yeah.
So that was something thing. I would definitely have started like the video.
Yeah. That's great. Yeah. Anyone else wants? Oh, the team on the back. Do you guys want to share something with what was the observations from the team doing the homework 1, part 2? Anything, any cool insights or strategies you come up or anything? Okay. Yeah. Well, that's interesting. Thanks so much for everyone for sharing. It's basically the main idea is if you're thinking that like something was really challenging, but you figured it out, it's very cool because the homeworks will become like more difficult. It's a very interesting skill to have, like you can debug everything on your own and think about like the problem through. The second one about strategies and resources, you think about what the most useful for homework 1, part 2. You can easily kind of incorporate it in your next set of homeworks. And finally, if you're thinking about some things that you could like do differently, like start earlier, maybe cooperate with your teammates, or maybe go to office hours like multiple times. You can also do that too. Okay, and now, before we proceed, we really want to do some real shout outs for people like top 10 submissions on Kaggle. You guys are really great. Like we saw so many people who hit the high cutoff. It's really cool. So you guys are great. And also this is like really cool because like some of you come up with such a cool names for your Kaggle submissions, especially the first one. I think the TAs loved so much. You guys are great. If you can continue doing that, we're really happy to read all of your submissions and names. It was so cool. Okay. Okay, now when we discuss this homework 1, part 2, some recap. Now we're moving on to homework 1, homework 2, part 2. The most important thing is like it will be a little bit more time consuming homework compared to the previous one. Number 1, you will have more epochs to run. And number 2, like the time per epoch would increase. So it means basically that you have to start a little bit earlier and also leverage the stuff and cooperate with your teammates, study groups, project groups, everything. Okay, and the goal of this homework bootcamp is to help you get started. The way how we want to structure this bootcamp is basically you guys can open the notebook. It's structured by separate sections. And now we will be going section by section. And you can think about like what kind of strategies you can use at every section. So if you guys can open the notebook, it's like literally Piazza post. The very first bullet point about the notebook. We can wait for a little bit so you guys can open. Does everyone open the notebook for the homework 2, part 2? Let's wait a little bit.
Where's
Huh? It's in Piazza Post. So like when I go to Piazza and I scroll here.
As a show of hands, how many of you guys have read the write-ups for
This is like, yeah.
either homework?
That's okay. Like
Yeah,
as long
yeah.
as you can guys open the notebook. This is a post number 573. If you can open the notebook and just like follow along. It's literally homework was released just like literally yesterday. So it's okay if you haven't read, but like at least following it through the notebook will be very, very helpful for you. So the Piazza Post 573, the notebook, the main notebook. Can somebody like, okay, guys, have you opened the notebook? Could you please raise the hands, whoever opened the notebook? Okay. Okay,
Open the starter or find things.
the main one, start the notebook. Yeah, the first one, yeah. Okay. Okay, so as we said, so we will be, how we'll be covering this recitation for homework 2, part 2. We'll be going section by section in the notebook and explaining like what kind of strategies you can use to make it more efficient and faster. The first one was talk about problem statement. What is the main task we're trying to solve in homework 2, part 2? So we have for this homework, unlike to the homework 1, part 2, we will have 2 tasks, face classification and face verification. What do you guys think, before we just like explain what actually this means, what do you guys think, what is like the difference between face classification and face verification? What does it actually mean, like to classify the face or to verify the face? Any ideas at all before we dive into this topic? Do you have any?
Verify. It is.
Okay, so verifying, like, you can give an example. Like, for example, we have,
Verify.
great, yes. This is the perfect example of face verification. So we have, it's like a face ID. When we open our phone, it just checks our like image, our photo, and make sure it compares with all the photos we have in the database and make sure like, yeah, this is the correct person. Face classification is kind of a simpler task. It's simply just like showing the face and we have to label it with the name of the particular person. So if we just look at this, we have 2 different tasks. For face classification, the model will get 3 images or like whatever, like million images, like thousands of images. And we'll perform a face classification, assigning a label for a particular image. For face verification, it's a different thing. We have a new unknown image, and the model should compare this image with some database or some catalog of unknown images and say, is this image present in the catalog or not? Do we verify it or not? So basically, the main difference of this homework compared to the previous homework, that you will have 2 separate tasks, but they're kind of related too. Okay. And then for the workflow of the homework part 2, so it's, you download a notebook, which is basically you did right now. You have to go and complete all the to-dos and then divide the experiments among the study group and kind of try to cooperate and find the best model. If you open your notebook, you'll see that you have like 5 different sections. The structure of the notebook is very, very similar to what you had in the previous homework. So we had with data loading and pre-processing. Compared to the previous homework, you will have images instead of audio. Then you have building a model. Then you have training and monitoring, test and Kaggle submission. And finally, a new section that you didn't have last time, but you have it right now. It's a model fine-tuning. So basically now we'll go section by section and discuss different techniques you can use at each of them. But make sure you have your notebook open because like we have lots of comments there too.
Okay, thank you so much. Yeah, so this is your first foray into computer vision for deep learning. And starting with data loading and pre-processing, it's going to be quite different compared to homework 1, where it was MFCCs and audio data based. So coming to this, right? In this homework, the data set and data loader part is really going to be super straightforward for you all. So unlike homework 1, where you all had to create your own data set class and sort of figure out the data loader as well, for images, we will be using the image folder class from Torch Vision, which really makes it very straightforward for you. So what it does is the file structure that we have, each image is already stored in a folder whose name is that of the class that we want to learn or predict, right? So, which is why we simply call the image folder class and send it to the data loader. And you don't really have to create your own data set class as you had to do for homework 1, right? So that's about that. And then coming to image augmentations. In homework 1, we said you may try, or it could be beneficial if you wanted to experiment with masking as a method of augmentation. But for this homework, image augmentations is a very, very essential and critical part of the homework and would make a significant difference in your peak performance and accuracies as well. So image augmentations, as we can see, like through this one image itself, you may be able to understand all of these are different versions and interpretations of a single source image from your data set, right? And those are the different applications that we can achieve. So why do we need augmentations in the first place, and why are they useful for data sets with images? Number one, emulating more data. So some of y'all did get confused, like we realized in the OS, where people thought we are actually increasing the size of the original data set, or there's something else happening. But what we are doing is emulating more data, where we are not really increasing the size of the original data set, but we are adding these transformations so that the perceived data set per epoch is different, and there are different alterations to the same image that the model sees. This leads to better performance and better training and more generalization. Second, prevent overfitting. Like you all might have seen, if those who did apply masking, augmentations helps avoid memorization of your data set, because unlike huge companies and organizations, we do not have unlimited data sets, and the available data and compute is what our bottleneck is, which is why adding augmentations, especially those that are meaningful, can help you prevent overfit and increase model performance as well. Invariance. So augmentations can be of multiple types. For images, there are mainly two. One would be geometric and one would be color. Geometric transformations help you add robustness to your models and increase invariance to things like rotation or translation within each image. So even if your face was in the top left of the image or slightly shifted to the top right of the image, that shouldn't lead to it being able to misclassify that thing, right? Which is why augmentations on both aspects need to be considered, not just color-based transformation, but also geometric. And better generalization, which is something that I covered, which augmentations would definitely help with. So sample augmentations. Augmentations are not something you all would have to create from scratch. It was much more challenging again in homework part 1 to create your own functions for time masking, frequency masking. For image-based, you can access the Torch Visions library and very easily call many of these augmentations. These are a few sample of augmentations that you could use. For example, color jitter, which would be a color-based transformation, random perspective, which is the geometric-based transformation, right? You have random crop, random rotation, random rotation. So as we can see, they can be extreme and they can be very minimal. They can help your model learn useful things and make them worse. For example, in random crop, if your task, as is in our case, to detect faces and identify faces, if we are sending in, say, the second image, right? There really is no face in that to be learned, or in any of the other ones. So do we think that random crop would be a good thing to use or not? So that is something we need to identify and figure out with augmentations, because augmentations are great, but they can have downsides as well. And if you end up using the wrong augmentations, you're training or showing data that is really not representative of your test data set, which will lead to worse performance. So yeah, as we look at this random horizontal flip, this would be a good transform because it is the easiest to implement. It doesn't really modify your image at all. And it is very representative of your final test data set as well, right? And with very low effort, you get a good representative augmentation. But on the other hand, maybe a random vertical flip for image classification wouldn't really be a very good transform, because it is highly unlikely that you will have sample images which are flipped vertically, right? So if you end up choosing augmentations that don't cover the entire expected range of test situations, it could hurt your performance. Normalization. So we did substral normalization in P1 and it helped in homework 1, and it was very useful. Similarly, for image-based deep learning, normalizing across the entire data set is something that ends up being very useful. It's a step that is not a part of your notebooks, but there's a link in the Piazza post as well on how you can find the mean and standard deviation and normalize your data. This is also part of the transformations, but yeah. So I'll go back to the previous slide, but just so that you all know, if you see transforms.normalize and the values inside, you will have to use this, but the values inside is what you would have to calculate yourself for the data set that we will be training on. That is going to be separate from this notebook. You all can just create your own file and define your own functions, pass the entire data set through it, and come up with the mean and standard deviation for the RGB values. And you can find a lot of documentation on this online, but that is just something I wanted to cover that is sort of separate from the first homework. So we would definitely recommend normalizing the data, because that sort of, again, helps improve performance. Like those of you who might have tried without and with substral normalization would have realized that normalization does help in extracting that half extra % at least. And then common issue, right? When you all do try running this assignment, and if you all do encounter this issue, transforms and how you apply them also matters. For example, this is a typical example of how you would apply transforms, but the sequence is not completely random or arbitrary. There are some transforms that expect the input to be a tensor, and those that expect it to be a normal array, right? Which is why it really matters which operations you apply after the to tensor call or before it. So that is just something you all should keep in mind. And along with that, in the slide itself, I have attached a link to the illustration of transforms, which takes you to PyTorch documentation. Yeah. Yeah, the scroll's not really working, but if you go on this link, it's like you would be able to see a bunch of different transforms and how they influence the images, right? So the link is right there in the slides for you all to access. For you all to access when you all start with your assignment.
So when you talk about normalizing it, are you saying that we should get the mean of all the images and then like normalize each image with that mean, or the mean of each respective image and normalize it with that?
Right. So in this or in general in deep learning for images, what you would do is you would try to get the mean and standard deviation, as you said, for each image in the data set. And then when we're applying this, during your data loading process, you would be applying it to each image as it's being loaded. But the calculation itself happens across each channel of each image throughout the entire data set. Yeah. Any other questions? All right, if no other questions, I guess we can proceed to the model section of this assignment.
So I'm assuming many of you guys won't have any CNN backgrounds over here, or like probably like you guys are beginners in deep learning. So let's just give a small insight on why we need CNNs. Just to clarify, we'll be using CNNs in this homework, not something else. But first slide is, yeah. Why can't we use linear layers for this homework? Can anyone tell me? Like, what's the reason why we can't use linear layers? I mean, it is information in the end.
There's too many dimensions.
That's true. That's one aspect of it as well. Any other things? Any idea? If you want, I'll give you a small hint.
Let's take also to the mic so that people say about it.
Oh, yeah. Cool. So I'll give you a small hint. Consider your image size was like 1000 into 1000. Okay, the pixel dimensions. And you have like 1 million hidden neurons in your first layer. What do you think could be the reason why we can't use this in a linear layer? Any idea? All right, so if you basically see this, if it's 1000 into 1000 size image with 1 million hidden neurons in your first layer, literally you'll be having 10 to the power of 12 million trainable parameters. That's quite insane. That's like bigger than most of our LLM models, right? So because of that, that's one of the biggest reasons. Like you'll have like extreme amount of trainable parameters. That would basically mean you would need like gigabytes and gigabytes, probably terabytes of your GPU VRAM to train it on, which is just like completely tough to do it on. So another thing is also the fact that for linear layers, you have to give your data in terms of a 1D array, right? But you know for a fact that images are of 2D array, right? So let's say I flatten it, make it into a 1D, put it in through my linear layer, and after I put it through my linear layer, I get some outputs. How will I reconstruct my image back to normal? It won't make sense, right? So that basically means that we are going to be losing our spatial features if we just use the linear layers. So what is the hero for this? CNNs. But what are CNNs? Why CNNs, right? Even The Rock is confused over there. Or if you guys want to know him, Dwayne Johnson. So CNNs are basically like really good in capturing your spatial patterns, especially they are well known for like handling your 2D images because you'll be like using something called kernels to basically convolve through your images. More will be taught on that on Monday's lecture, I think, or Monday or Wednesday, not sure. But yeah, they are also known to be a good feature detection kind of models because you'll be using kernels for it. And the most important bit is you're sharing your parameters for your architecture. So basically, you'll not be needing like 10 to the power of 12 million hidden parameters because you're using kernels in this case. You'll be sharing in your like weights, which will drastically reduce the number of parameters in your model. And the other good thing about CNN is the fact that you're using kernels to like basically convolve to the images. It gets a new like addition that it's basically translational invariant. More will again be covered in the lecture, so I'm just giving a high level overview for you so that you can understand what's up with it. But again, even though we are going to be using CNNs, just CNNs is definitely not going to be enough for us for this homework. Because most of the time, like the data is going to be like huge. There's a huge amount of chance of you to get overfitting. And to resolve overfitting, you can do augmentation techniques, but again, augmentation techniques will not always help you out in it. They are super important, so you should play with your augmentation techniques as well. Then you can apply regularization techniques, but again, it's like there's a lot of like things that go on. So it's like using only CNNs will always not be like good enough for this homework at least. So let's go and see. Yeah, so we need to basically get more complex architectures that find different ways to converge the model and mitigate your overfitting. So the main thing is I wrote over here, if you see clearly, it's not avoid overfitting, but it's mitigate overfitting. Because in this homework, it's kind of expected that you will overfit your model. There will be a time when let's say your training accuracy will be like 99.99. Your accuracy for your validation might be like 78%. But even if you still train it, you might get that 2% leeway. So that's why I'm saying mitigate overfitting and not avoid overfitting, because overfitting is kind of expected in this homework. So this is just a small heads up for everyone for this homework. Now, some of the good models for this homework, especially ResNets, really good. I think some of the recent architecture is Conv-Next. That's also a good architecture for your homeworks. And SE ResNet, and there may or may not be a magical architecture that might help you in this homework. Not going to say anything about that, but that's for you guys to find out online or through some other ways. So I'll not be able to talk about all the models over here. So I'll just talk about ResNets, give a small touch upon the Conv-Next, and then let you guys decide on what to do next. All right. So the main aspect is you have to go read the paper and understand the paper. That's the most important part of it. But when you keep going through the paper, you'll understand just like there are just basically two things that they'll talk about, especially in their model. That is basically one thing is the blocks that they use and why was the architecture like useful. That's basically the main aspect of the model, right? So for ResNet, now you just go to the paper, read the probably like 8 pages of boredom, like things that they have written on it. You'll figure out that ResNet just introduced 3 things in it. That was basic blocks, bottleneck blocks, and basically residual connections. And the main aspect of the paper was residual connections. I hope everyone is fine right now. If not, it's there. But yeah, so let's start talking about the residual connections. So especially for your homework ones, I think you guys know that when you made the def forward function in it, your data flows through each layer sequentially, right? Like it just goes from one layer to the next layer to the next layer. Okay, so residual connections, or the other name for it is called skip connections. They provide another path for the data to reach the later part of the neural network. This is done. Let me go here. Yeah, so this is done by just basically taking in your input, mapping it to a identity, let's say vector or whatever you want to call it, as X, and then you perform that basically going from one layer to second layer to third layer to how many ever layers you want, and then you basically just add the identity mapping to it. That's basically pretty much residual connection. It's just like you're adding what was at the start to after you basically went through like some X amount of layers. Again, that was like the main aspect of ResNet. Apart from that, they have something called basic blocks and bottleneck blocks, but we'll talk about it. But first of all, I want to ask, how does this help? Like, why will this help? Anyone has any idea on that regards? Like, why does residual connection help per se? Like, why would it help? Like, what makes it so great?
Because it won't perform much worse than the previous algorithm.
It won't perform.
It becomes something from the previous layer.
That's a nice way to look at it, I would say. That's good. Any other answers? Exactly. So, especially for like, let's say CNNs, the chances of vanishing gradient is like a lot more. So when you go through like different layers, especially, what happens is that like your signal gets weaker. And by signal, I just basically mean like the trainable parameters in yours, it keeps getting weaker. And when you go through a gradient descent, when it gets weaker, there's a chance of vanishing gradient. For that to not happen, you basically add up the identity mapping to it to ensure that the signal is still strong when you do your gradient descent and your forward propagation. But yeah, I would say this image is basically the perfect representation of residual connections. Like, if you just try to convert this to code with your forward function, this will literally tell you like what it is. So basically, if I have to explain you the image, it's like, this is your first layer. X is basically, you know what it is like basically just the input that goes inside. So you go through your first layer, you apply batch norm, you apply ReLU, you go to a second layer, apply, you can apply batch norm or ReLU, or before that, you take X, put into an identity vector, and then just add it along, and then you can do your calculation. So again, that was the main aspect of the ResNet paper. Apart from that, they had something called bottleneck blocks and basic blocks, which I'll be talking in more depth. So first of all, basic blocks. All right. Does anyone know how many ResNet architectures are there? Like in the original paper, there is ResNet 18, ResNet 34, ResNet 101, ResNet 152. 4. All right. So where does basic block come in? Like, which ResNet architecture does basic block come in? Any idea? Hints? It's the starting one, ResNet 18, where basically the basic block was introduced. Okay. So what is basic block? Basic block is just nothing but like two convolutional layers stacked with each other, basically just regular 3 into 3 convolutional, followed by batch norm, ReLU, and then another convolutional layer, and then again a batch norm and ReLU. And like in between them, there is a skip connection. That's pretty much it. That's a basic layer. Now, the bottleneck layer, which was another one of the important aspects of the paper, I would say, is especially, I would say, like happens in ResNet 34, 101, and 152. Over here, it's again, they have something called a point-wise convolution and a depth-wise convolution. Does anyone know the difference between both of them by any chance? Point-wise, depth-wise. Okay. So what do you think 3,3 indicates over here? I mean, I'm pretty sure like most of you guys will not know it because like we haven't even touched upon CNNs right now. So it's really fine. So basically over 3 into 3 is basically the kernel size. Kernel size is basically the amount of pixels you want to like convert through the image, basically the size of that. So there is something called a pointwise, which is basically making your kernel size 1 into 1, which will mix in your values from your channels and from your depth. Basically, that's X and Y axis of your images. But again, like I know you won't understand it right now, but this bootcamp, I hope you guys can like go through this bootcamp again after like the lectures are done so that you can understand what I'm saying. But yeah, that's basically pointwise. Depthwise is nothing but like having a 3 into 3 kernel where your in channels, basically in channel dimensions, it won't mix through your in channels, but it will mix through your X and Y, the depth of the image itself. So that's pretty much it. And bottleneck, what it does is it takes the net input, makes it go through a pointwise convolution, then goes to another depth-wise convolution, followed by making the channels, let's say from 64 to 256, and then just put in a skip connection and then just go through another layer. So this is just like a small coding example. Again, don't use linear for your homework. If you do, bad results followed by probably you might need like 1 terabyte of VRAM to train it. So this is just for an example purposes. I didn't want to show the code over here, or else like it'll be easy to get your high cutoffs. Again, this is for bottleneck. Again, just for you to have a look through at it. It's just what I explained again, just going through like the different layers. But over here in this code, it doesn't show the point wise and depth wise. So I just wanted to point that out. Apart from that, it's just the same thing. Again, don't use linear layers, I would say. Now, like I said, oh, okay. So there are like different type of Resner architectures. You can go have a look in the paper itself, and then like probably go to the GitHub code also, have a look at it, like how they're doing it. That's also a good way to learn how the architectures are. And like after that, you can come and code it by yourself. For this homework, we explicitly say that you have to make your own code for it, because we don't want you to just go to, let's say, ResNet's GitHub repository, copy the entire code, paste it, and be like, yeah, homework is done. No, you'll have to basically code up your architecture from scratch. And there's a reason why we had kept parameters limit for that, is because you will you'll have to basically make up your own blocks, your own layers, and your own like number of channels. You have to like define it by yourself, and then basically do your network architecture. So just a point of note, like there are different type of Resner architectures. You can go have a look in the papers. ConvNext, same thing. There will be like different type of ConvNext. So for this homework, we recommend something called ConvNext Tiny, which I'll just touch upon it. There is SE ResNet as well, which you guys can have a look by looking into the papers. There is a magical architecture that I just told. Now, to find that, we are not going to tell you at all. It's something which you'll have to like probably dig in deep. And if you dig in CNNs, you'll just get to know which architecture it is. A lot of information. I hope I didn't stress out anyone, just in case, right? So breathe, I would say. That's the first thing. Breathe, take a moment. A lot of information was processed. Take in the positive vibes, remove the negative vibes, and let's reduce stress a bit, hopefully. So I'll just talk about the general architecture flow right now. Basically, we talked about blocks, and like there's something called stage, which is basically like consists of only blocks, and that's how your basically general architecture flow will be. There'll be something called stem, then a stage, and then within stage there'll be many blocks, followed by a classification layer, which will be used for your classification task, but for your verification task, you'll be removing out the classification layer completely. So again, ConvNext is a pretty new architecture. It's a little bit difficult to train with. It takes a lot of time to train. You may or may not get good results with it. That's an ablation study for you and your study groups to decide. Again, we recommend something called ConvNext Tiny over here, which has less than 35 million parameters to play around and see how it works. And the intuition behind that is basically next to MobileNet V2, which you guys can have a read on and see how it is. Again, like I said, the general architecture flow, you'll have something called STEM, which is basically just your initial augmentation. I mean, not augmentation, but it's like just making it go through one small layer of convolution, followed by something having a stage, which stage has multiple blocks. And then you have FC layers. But for your classification task, you'll have all three of these, but mostly for your verification task, you'll be removing out this part. Just a small point to be noted. And yep, that's pretty much it for building a blocks. Again, I just gave a small 2 lines about what is depth-wise convolution and point-wise convolution, so you guys can get a small heads up on that. So let's go on to training and monitoring, which
Guys, you can maybe get pizzas and then we'll literally have like 2 more sections.
Please take one first, so then
Can we
everybody
all-
can get one.
Can someone say for us?
Hello.
Oh, we were muted that whole time. Okay, so now we will move on to the last part of the notebook. If you guys scroll down to the very bottom, you guys should see like face verification. This is probably like the coolest part of the homework in my opinion, because this is pretty much what your phone does when you try to log in. I think that's like, at least in my opinion, this is the coolest part. So yeah, so how is this different from face classification? So like if like you're in the mindset of we've just done all the first part of the homework and you submit that to Kaggle, what you've done so far is given the input data of just like people's pictures, you've correctly labeled who is who. This is similar to homework 1, part 2, but instead of speech, now it's 2D images. Yeah, so this is just a face classification problem, and you can kind of understand that hopefully. So now face verification is a little bit different, and it's a different problem, right? Because now you want to say, is this the same person I've seen before, or is this someone new? As in now you want your features to not just be able to say who is Mark versus who is someone else. You want them to say similar looking faces should be grouped close together. People that look different should now like be far apart as per your model. And that's kind of a new problem that we're trying to solve now. So, and you can kind of visualize that as in face classification. All we cared about was just, can we accurately predict each face to its like what its name is supposed to be? Versus now we care about, can we group similar faces next to each other so that when we see someone new and they're not the same face, we can say they're not the same as like who you are. As in like, if you use your phone, you want your phone to only say yes to your face and not someone else's face. Does that kind of make sense? So we want to learn discriminative features that separate one input from a different input. Yeah, so like, I guess, how do we learn these discriminative features? And a different way to like pose the same thing is, like, how can we maximize the agreement between like positive pairs? So if I give you a picture of my face like this and my face like a little bit like that, it should still be able to say you are the same person, as opposed to if it's my face and like, I guess your face, to not be able to say it's the same. So how can we minimize the agreement between two different faces, maximize when it's the same face? That's where contrastive losses come into play. And essentially the point is we use some sort of like similarity score to like rank how similar are these features that we're learning. If I have two of the same faces, we want this similarity score to be high, as opposed to if we have two different faces, like slightly angled, slightly different, we want that similarity score to be lower because they're not the same face. And we want to learn this to maximize like faces that are the same. Does that kind of make sense? This is going to be very important for the part 2. So, yeah, there's kind of two general approaches to this. One is you just train your model. These labels correspond to the face classification task, where you have this face that belongs to this person. Take those and perform some sort of contrastive loss, where you can sort of score whether these features that you are learning are matching up with the actual face features themselves. That's one way to just do these both simultaneously. The other way you can learn better discriminative features is separate these two tasks out, which in the notebook is kind of structured that way, but feel free to do whichever one makes sense to you. So in the first one, you just do the first task, which is face classification. But then after that, take the same model or take a new model, just take the model and do contrastive loss as a separate fine-tuning step. And that's kind of how the notebook is structured if you take a look at it. Kind of separate into these two sections. And this extra fine-tuning will like help you reach the high cutoffs for the verification task. Yeah, and there are a couple contrastive losses out there. I just wanted to give you guys like a brief like idea of what it is. The math we will skip for like a different day, just because I feel like it's not as helpful. But there are a few, and there's more out there, so feel free to take a look. These are some papers that go into it. There's also hidden slides in here if you take a look later that kind of go through some of the math as well. Yeah, did that make sense? Yeah. Are there any questions about like why this is or what this is or anything like that?
Can you explain the difference between the two approaches?
Yeah.
again?
Yeah. So here we do our normal cross entropy loss, which is what we've done in homework 1, part 2 for classification tasks. The cross entropy is a classification loss function. But then simultaneously, we also do this contrastive loss to maximize the similarity of our features when we have the same face and minimize the similarity when we have different faces. That's going to help us then help the model learn better features. And then in this task, we focus on just the classification. So it might not have the right features for classification, but then we fine tune those features to make them more towards the verification task. Did that kind of make sense?
Yes, and in the previous slide, is the yellow circle like addition of the losses?
Yeah. And then what you can do is you can set some weight. So we compute some cross entropy loss, right? Then you can weigh how much you want to take into account your contrastive loss. If you want it to be like 50% or like 10%, you can pick that, and based on that, you'll get different feature representations. So that's something for you guys to play around with.
Okay, thanks.
Yeah, is there any questions? If not, that concludes the homework 2 boot camp. Now we can just ask questions or work on anything you guys want. Should I stop the share?
Now, regular office hours, if you have questions.
I'll just stop the share.
Yeah, let's.
Stop.
I have a question related to project group. Can I talk to you guys, one of you guys?
Oh yeah, well, let me, yeah.
Yes. You can just talk with him separate.
Okay, yeah.
Yeah, can you stop the recording also, I guess?
Oh, yeah, give me 1 second.